Okay, so I know we didn't quite finish some of the notes, and I just wanted to explain like this last problem so you have that available for your notes in case you need some help with your homework tonight. So we did talk about this. We talked about the general multiplication rule, and really what that is just a manipulation of our conditional probability formula. So we know that the conditional probability of A after B is the probability of A and B over the probability of B. And all we did to come up with this general multiplication rule is we just multiplied both sides by the probability of B. So it's on now like the right-hand side that we have. And then the probability of A and B, the numerator of our conditional probability, is equal to the probability of B times the probability of A after B. So it's just manipulation of that same formula. It's not anything new. The special multiplication rule is the probability of A and B. If we know these things are independent, we can just multiply the probability of each of these events occurring individually. And really what that comes from, again, is the conditional probability that, like, the conditional probability doesn't impact the probability of that event happening. So we can end up multiplying those two events because they're happening in succession. So like the probability of flipping heads and the probability of flipping heads again is independent of each other, but the probability of having two heads in a row would be 1/2 times 1/2. So those are two independent events. The probability of having two heads happen in a succession of two flips would be 1/4. Now, we have lots of independent events that could happen. So if we have multiple ones, then to find the probability of all those things happening would be the individual probabilities multiplied. So we can extrapolate this with lots of different ways. So we only have one more example to look at. So if we know right now we're having a box containing 4 red coins and 5 blue coins, we're going to go through a couple things of probabilities of with replacement and without replacement. So right away, knowing the probability of drawing a red coin, well, if I have 4 out of the 9 that I have, the probability of drawing a red would be 4/9. We could also find the probability of drawing a blue coin, which would be 5/9, which makes sense. Those two things should add up to 1 for a sample space. Our next question is the probability of drawing 2 red coins without replacement. So this means that we're looking for the probability of a red and another red, which means that we're kind of using this special multiplication rule of looking at the probability of like A and B happening, which we're going to define as red 1 happening and red 2 happening. So this would mean that we're looking at the probability of red 1, and then the conditional probability of drawing red 1 after we knew we already drew drawing red 2 after we knew we already drew 1 red out of the bag. So at this first part, we know the probability of drawing 1 red, that's 4/9. But now that we've drawn 1 red out of the bag, that impacts, since these are now dependent event, we're not replacing them, that impacts our conditional probability. So if I already take 1 red out of the bag, I'm left with 3. But I'm also left with now 8 coins because I already removed 1. It changes the total as well. So the total probability of drawing a red 1 and a red 2 would be 12 over 72, which is 1/6. The second question is looking at it with replacement. So if I'm putting that coin back, now these are independent events. It doesn't matter what I drew previously. If I replace it, the probability of drawing that same thing isn't impacted by what I did beforehand. So if I'm looking for something with replacement, and I'm looking for the same question, the probability of red 1 happening and a second red happening, that means that my probability of red, the first red, is still 4/9, but the second probability that I have of drawing a second red after I drew 1 red, if I put that red back, it's not impacting the total number of coins, it's not taking that red out, so that's still 4/9, which means my probability will end up being like 16 over 81 or approximately 19.8. The last thing is that we can't have mutually exclusive events and having independent events. Really what this means is if I have mutually exclusive events, that means that one event happening dictates that the other event can't happen. So by definition, having a mutually exclusive event makes it so that the other event won't happen. If I flip a coin and I know that I flipped heads, the probability of flipping tails after I know I've already flipped heads is 0. That does impact. The probability of flipping tails originally was 1/2. Now the probability of flipping tails after I know I flipped heads is 0. So those two things are dependent events if they're mutually exclusive. I know we've been throwing around that flipping coins are independent events, and that's true if we look at flipping coins in succession. But if I'm talking about one coin flip, those are mutually exclusive, but then also in like dependent events.